We acknowledge the first Australians as the traditional custodians of the continent, whose culture is the oldest living culture in human history. We pay our respects to elders, past, present and emerging, and we respect their cultural heritage, beliefs and relationship with the land. We extend our respect to all Aboriginal and Torres Strait Islander people here today. They share the memories, traditions and hopes of the traditional ancestors with the new generations today and in the future. We would also like to thank them for looking after this land for thousands of years.
Good afternoon, everyone, and welcome to our next session of the Earth Science Week program. So my name's Karen and I am presenting for Earth Australian Environmental Education. You may have noticed me throughout the other sessions because I'm also was coordinating this event on behalf of Virtual Excursions Australia. And a big thanks once again goes out to Geoscience Australia for funding all of these programs to enabling them to be run for free throughout today. So dynamic Earth is the session that we are talking about today. So what do we mean about this dynamic Earth? So let's have a think. Okay. So things are constantly moving. We're going to be having a look at the motion, the engine that moves all of these plates around, but also what rocks are. Do you know? Do you know what makes the difference between a rock and a mineral? So we're going to have an opportunity to do lots of questions as we go throughout as well. So if you're at home or in the classroom, get some of your questions ready. If I ask you a question, you can put it into the chat that I'm just opening up for you now. But questions that you have specifically for me, you can put in the Q&A. Now, I have been collecting rocks my entire life. So it's something I've always been fascinated in and something that I have continued to want to learn about. When I was at primary school, I remember doing assignments on volcanoes and learning and exploring there. At high school, I did science, looking at chemistry, and at university, I studied geology and paleontology. And I was lucky enough to then work at the Australian Museum in their science communication department and was able to work very closely with our mineralogy department, which was very exciting. So personally, I've been collecting rocks for a very long time and wanting to learn more about them. So hopefully this is part of your journey into discovering more about Earth science, dynamic Earth, and what you can do to maybe find out a little bit more. Okay, I've got some slides that I'm going to share with us today and we'll go through those. We're going to start looking at the rock cycle. So that's a really interesting one. You might have heard before of something called the water cycle, which is how water moves, but actually there is a rock cycle as well. And it gives us of how our different rocks are formed. So I'm going to show you the rock cycle and then I'm going to come back to the table and show you some of the rocks I've got on the table here and how they link to the rock cycle. So let's just share the screen. Okay, so this is an image of the rock cycle here. So what we've got is three groups of rocks. You may have heard of these before: our sedimentary rocks, metamorphic rocks, and our igneous rocks. So igneous rocks, or our volcanic rocks, are made in or around volcanoes. Then we have a process called weathering, and that's when rocks will break down. So these rocks, that when they're breaking down, those small particles go through a process of sort of transportation and deposition, usually in our lowest part. So our rivers, our oceans, where those sediments under time and pressure push together and form our sedimentary rocks. And then deep inside the earth, under more pressure, we get our metamorphic rocks. And they are those igneous or volcanic rocks that have, or sedimentary rocks that have been changed. Okay, excellent. So let's have a little look at some of those. We'll leave that one for a moment and we'll come back to what makes the difference between a rock and a mineral. So on the table here, I've got some of those igneous, metamorphic, and sedimentary rocks. So I'm going to have a look at them on the table, and I might hold them up to make it a little bit clearer. My lighting is making everything look really, really pale today. So this side is our sedimentary rocks. So the first one I've got, if I hold it up even closer, let's see if it's going to focus, has different grain sizes. It's not going to focus for me today. So what you might see is some pebbles and some very small grain size there. So that's called a conglomerate, where it's got different size. Then we've got our sandstone. Now, sandstone is essentially grains of sand all cemented together again. Really common. It's rough, feels like sand, of course. And here we've got a limestone because it's actually got some fossils in it. So often we get a fossil limestone. Now, sandstone under heat and pressure will then change into something called quartzite. So it looks a little bit different. It's different size grains. And limestone under time and pressure turns into marble. So lots of times marble's used in things like bench tops and statues and those kinds of things. And of course, we've got a lot of building materials that are made out of our sandstone. Then we can go to this section here, which are our volcanic rocks. So this one here is actually a volcanic bomb. We can see larger crystal sizes in the middle there, surrounded by our sort of basalt, which was our lava, which was thrown out of a volcano. For those of you that play Minecraft will be very familiar with this one here called obsidian, which is volcanic glass. And that's where lava is cooled very, very quickly. And it gets a very, very sharp point. So this was often traded and used for tools, make spears and knives all around the world. And it still can be used to make a very sharp edge today. Another one here, granite, which we're going to talk a little bit more about later on, is another one of our igneous or volcanic rocks. And if I can show it up, you can see a little bit of reflection coming off it there with the different minerals that are inside this rock. So granite sometimes comes in other colors as well. Again, very common use for a building material. And then this one here, we've just got some basalt, which is essentially called lava. Okay, let's just have a look back at our screen. And we're going to have a little conversation about the difference between a rock and a mineral. But I want to see if you guys can have a little guess. So if you want to pop in the chat what you think the difference between a rock and a difference between a mineral is, and maybe even the difference of a crystal and an element. So these are some different words. Elements you might have heard of, crystals you've heard of, rocks, and minerals. So what are the differences can you think of between those things? I wonder. Kids say rocks above the ground, minerals below the ground. I love that explanation. That is not one of the definitions though, but I do love how you're thinking. Rocks are minerals combined. Yes, I like that one. Let's see if we've got any others. Yes, we've got another one. Rocks are made of minerals. There are lots of differences. Minerals are just one element. We're going to mention elements. Rocks can change and minerals cannot. Minerals are a lot more rare compared to rocks. Tony says that minerals have been in volcanoes for many years. Minerals are more rare. Oh, great responses. Crystals are made up of minerals. Some elements are minerals. Yes. Crystals in water that become gases and then over time other minerals crystallize. Minerals have special healing powers. We've got lots of responses there. Okay, well, let's just have a little look. I'm going to show you a couple of things first. And then we'll come back to some of the specimens I've got on my table here. Okay. Okay, so this is a really simplified example of the difference between, so what are minerals and what are rocks? So minerals are made up of elements, things like copper or gold, oxygen or silicon, and a mineral can be made up of a single element or a combination of elements. For example, calcite, which I'm going to show you in a moment, is limestone, is found in limestone and can be calcium, carbon, and oxygen. And the one we're going to look at now is granite, because that's the one I showed you before, that really classic white, grey, and black stone. This is an igneous rock or a volcanic rock, and the granite is made up of quartz, feldspar, and mica. And those little black bits that were reflecting, that was your mica being picked up by the light of the camera. So just imagine it's like you're making a cake or a recipe, pancakes or biscuits. You would combine different ingredients, your different minerals, and those different combinations give you a different product. So sometimes it's a different mineral, maybe changes the color. Sometimes it might be that you leave something out. So if you didn't put eggs in or you added eggs, you get a different rock being formed. So just imagine that your ingredients are your minerals and your rock is the product that you're making. So to make calcite, we needed the calcium, carbon, and oxygen. To make our granite, we needed quartz, mica, and feldspar. Okay, so let's go back and have a look at some of these. And I've just got a question in the chat. Rocks and minerals that have been pressurized. So I like that you're thinking about what's going on inside the earth, and there is a lot of pressure. So we've got our minerals, and those combination of minerals form our rocks. So let's have a look. We mentioned a mineral called calcite. So this is our calcite here, made up of elements. And the other thing we'll look at as well when I'm showing some of these is different crystal shape, because some of these rocks and minerals can be identified by their shape and or their color. So this one here called calcite forms this particular rhombus shape. So it's like a rectangle that you've kind of squished on its side, or a cube that it's squished on its side. And it will form this crystal, and it will break down these different planes. So sometimes you can get them bigger or smaller, but they like to form that shape. Another example is one of those single elements is copper. So this is a piece of what we'd call native copper, and it's a metal. It's formed in that shape, but copper is definitely involved in lots of different other minerals as well. So if we look at this one here is called malachite, and it gets its green color from copper. So you can see that that copper would be one of those ingredients in malachite. Okay, I've got a couple of other things to show you while we're here, just to look at those different crystal structures as well. So some of these will be really common ones that you've seen before, but I want to show you either the color or the crystal shape. So this one here, you can pop it in the chat if you know what it is. This is quite a big piece. We can see how it was formed. We've got the outer rock in the grey here, and then we can see the clear crystals, and then we can see the purple crystals. So as the liquid would have been coming through, the crystals would have grown. And the purple color, yep. Oh, we've got excellent. Someone said it's a geode, so it would have been inside a geode. And the purple is what we have here, is our amethyst. But amethyst is actually a type of quartz crystal. Now, this is a smoky quartz crystal, so it's not clear. But you might notice that it's making a point here. And the point that it's making is that it likes to make these six-sided points. And I've got Thomas here wants to have a job like this when he's an adult. Well, start collecting rocks, start doing your research, Thomas, and you will get there. So it likes to make these points. So given enough space and time, they like to create these points. So quartz crystals or quartz points, you'll see that. And if we look closely at our amethyst, I'm going to try to pass it really close up. Now it's gone blurry, but you can see that it's trying to make those points as well. Let's see if I can zoom in without, maybe I'll try to zoom it down here. There we go. So we can see that it's trying to make those six-sided points as well. So some minerals, given enough space and time, they like to make certain crystal shapes. So remember these amethyst or your quartzes like to make these six-sided points. But then we can again have a look at our calcite. and they're making those rhombus cubes. And my favorite is a metal called pyrite, often called fool's gold, and they like to form cubes. So given enough space and time, they form these cubes. So one of the ways that scientists do identify these different minerals is by looking at their color and their crystal shape. So sometimes you think things have been cut, and sometimes they have been. Sometimes they've been dyed and their color can be changed. Sometimes they can be carved and cut in the same way gemstones are. But a lot of these like to form certain crystal shapes, given enough space and time. Okay, let me just flick back to the slides. Oh, sorry, I had a couple of questions. Let me have a little look first. We had lots of responses to amethyst. Can you show a piece of rose quartz? I actually can, AJ. So this is rose quartz here. It's really hard to see at the moment because of the color. So it is pink. And rose quartz, even though it is a quartz, doesn't make the crystal shape. It always tends to form in that more dense shape. And let me see if I can zoom it in here. Yeah, very hard to see the color there, but it is pink, hence the color. A question regarding, does the value change various types of quartz during to the color? Yeah, it can do. So you've got ones like citrine that are an orange color that are generally rarer, and they tend to be more valuable. So it can certainly with amethyst as well. The darker the purple color tends to be considered to be more precious. So it really depends. You know, it's all a little bit on supply and demand and where things are found, but generally the deeper colors tend to be a little bit more valuable. Oh, I don't have a ruby or a sapphire to show. We've got a couple. Can I show some fluorite? Oh, I don't have a piece of fluorite on me at the moment, but I do. I have some in another box, but it's just not within arm reach. So I'll see how we go. At the end, if we've got time, I might be able to get run off and try to find a few extra bits for you. What rock is the rarest? Oh, well, that is a really interesting one. So you've got things like, and someone else was mentioning crystals from space. You get things like meteorites that are coming in. And so when they land, they're actually considered quite valuable, that they're trying to find. And when they get those meteorite impacts, you get lots of things sort of blown off and the changing of the sand around it called tectonics. So it's they've almost turned into glass. So they're often considered to be quite rare as well. But it really is depending on, sometimes it's a color variation, sometimes it's a location about where things are found. I visited a friend yesterday and he showed me some amazing argyle pink diamonds. And so the color variation of the diamonds, sometimes yellow, sometimes pink, then can make them very rare. So yeah, there is a lot of amazing high quality and rare things out there. But let's move on. Otherwise, I'll be running around trying to find different rocks for you, and we won't get to see some of the other parts of the program. Okay. Oh, sorry. Let's just go back this way. My screen's doing all sorts of strange things for us today, so apologies there. Okay, so the periodic table, if you haven't had a look at it, absolutely do. There's all of those elements. So we've got those single elements like copper, gold, and silver. But then you've got those combination of those elements, say like quartz that we talked about, which is silicon dioxide. So silicon and oxygen combined to make that particular type of mineral. Some minerals will actually fluoresce. So if you do have a little rock collection and you've got a UV light, give it a try to see what minerals you might have within those rocks that actually fluoresce, so they glow a different color. As I mentioned, you've got those different cube shapes or pointed shapes, or the rhombus shapes like those calcites is another way scientists can identify different rocks. But also there's something called the Mohs hardness scale, and diamond at the top being the hardest mineral, all the way down to something like gypsum or talc, which you can actually break up with your hand, and it gets harder. So some things you can scratch with your fingernail, some things you need a coin, some things you need glass or a knife or a nail. And essentially the way they've worked it out is the one above can scratch the one below. So it's another way that we can classify different minerals. We can also use something called streak, which is using sort of a white tile and scratching the rock or the mineral on it and seeing what color is left behind, because sometimes it's not the same color that the mineral looks. So there are different ways that they can be identified. Of course, they can use that chemical structure and looking at the elements from the periodic table as well. But a lot of the time it is using observations of shape and color and things simple like hardness. Okay, so what's going on? How does this dynamic earth process happen? So we need to now go inside the earth, deep beneath your feet. So the earth is made up of layers. Okay, so imagine that the surface is the crust that we are standing on, and that can be in some places where it is pulling apart very thin, all the way up to about 100 kilometers thick at some of our highest mountain ranges. Underneath that layer is our mantle. Okay, and it is not, it's kind of a liquid, it's kind of not, it's a molten material. So where some of the crust is being recycled, that's where we have sort of molten bits of rock, and new crust is bubbling up and forming. And this is the layer that feeds our volcanoes. And it is constantly moving as well. Then we have the outer core, which is liquid metal, and the inner core, which is solid iron or nickel iron. They estimate that the inside of the core is about the same temperature as the surface of the sun, about 6,000 degrees. So you can just imagine. Now, this inner core is solid, even though it's hot, because of the pressure of everything else above it. And that is making it solid. And the liquid outer core is really important because that is giving us our magnetic fields around the Earth, which is making one of the ways that Earth is actually can be inhabited, because it is still moving. It is still hot. It hasn't cooled down. Okay, those of you that were with us this morning would have heard us talk about plate tectonics and how these plates are moving around. So if we look at Australia here, we are in the middle of this plate. So you would think that we wouldn't get a lot of earthquakes or those kinds of things. But even while we've been sitting here today, there have been earthquakes happening in Australia. They just tend to be very low on the Richter scale. So things that maybe only the sensors can hear or pick up, but they are certainly happening. Last September in Melbourne, we had an earthquake that was 5.9. In the late 80s, there was an earthquake in Newcastle that was even higher, that did quite a lot of both damage to property and life. But considering we're in the middle of this plate, we are pretty what we call geologically stable. Whereas if we have a look at the edge of the plate, we've got New Zealand is essentially across two plates. And over time, it is going to be ripped into smaller islands. We are pushing kind of northwest at about 7 centimeters a year. So it doesn't seem like it's very fast, but it is one of the fastest moving, Australia is one of the fastest moving continents on Earth. So that's 7 centimeters. Just imagine over a year, over 10 years, over your lifetime. What about since the time of the dinosaurs? What about 200 million years ago? So over great periods of time, things have moved quite a lot. And essentially all those continents push together and pull back apart and push together. And it's this plate tectonics that is happening inside the Earth that's important. Okay, some of the ways we know about this is by looking at the fossils, but also like looking at the rock layers. So if we have a look behind me, you might notice a few things. So if we look at the rock layers here, some rock layers have fossils in them. Some rock layers are made up of different materials, and we can track those rock layers. So we can see that over time, they may drop and move, but we can map them across the Earth. And that is what scientists were doing. They were looking at the different rock layers from other continents that are nowhere near each other now. And when they looked at certain fossils, they matched. And when they looked at certain rock features, they matched. So when they pushed those back together, like, oh, this makes sense. But for a very long time, this idea didn't exist. This idea of plate tectonics was just a little bit confusing. So I want to get you to have a little think about how this engine, how this is moving inside the Earth. So I'm just going to show one more slide and then we will have a look. So we've got our solid inner core. I'm sorry, my screen is just not sharing very well today, so I apologize, everyone. Let's get back to full screen. Okay, so we have our inner core, which is that solid metal, our liquid outer core, and then our mantle. And inside the mantle, we've got something called a convection cell. Now, these convection cells happen in lots of different places. They're happening in our atmosphere. They happen in the room. They happen, you might have convection ovens. That's because the air's and the heat's moving inside the oven. And it's all about the idea that heat, something that's hot, rises. And as it gets to the surface of the crust, it pulls apart. And as it cools, it sinks. So this circular motion, and I'll get you to put your hands up and do it as well. So just imagine your hands are hot on the outer core, and as they go up, they're pulling mantle up with them, but they're hitting the crust where it's cooler, and they are pulling the crust and they are sinking. And as it sinks back down, it heats back up, and what's going to happen? The hot moves back up again, hits the crust and the lithosphere, pulling it apart until it sinks again. So we get this constant motion called a convection current. Now I'm going to demonstrate that for you today, but I'm not going to use heat. Okay, I'm just going to move my rocks away so I don't make a mess. So I'm not going to use heat. I'm going to use what's called a catalyst. Now, a catalyst is something we use in science to start a reaction. Let's see how much mess I'm going to make. So what I've got here is a bottle. You can do different sizes. And then I've got food coloring and water at the bottom and oil at the top. So I'm going to, well, maybe I'll be able to hold it up. That might be the easiest option. So I'm taking the lid off. And I've got an Alka-Seltzer tablet. So these are fizzy tablets, and this is going to be my catalyst for today. Unfortunately, I have broken it. And I've got my tablets sitting in the bottom. So this is being my heat. So at our pretend heat layer, we can see the bottom bubbling up. And as it rises, it's releasing gas. The gas is escaping out of the top. If I had the lid on, this would eventually bubble and explode. But we can see those big bubbles coming up. It's releasing gas, and then it is dropping down the side. So this is the same idea that I've just made a convection current here. Something's going up, it's releasing the gas, and it's dropping back down. Inside the Earth, it's heating up. As it gets to the surface, it's cooling down, and then it's dropping back down. So it's this idea of this convection current constantly moving inside our Earth. Okay, it's bubbling away very furiously. And I will give some instructions of how to make these at home or at school as well. So it is quite fun. It's often called the homemade lava lamp. But again, we're not using heat. Once you finish with it, do put the lid on, because if you knock it over, it does make a lot of mess. So I've got to be super careful that I don't knock it over before my lid goes back on, because it's got a lot of gas still moving around there at the moment. So I'm going to put that down there safely. And I've just seen a couple of questions that I'll get to before we go back to our slides. So we had how many different types of diamonds. So diamonds, they range in color, but the diamond itself it's one of a kind. What other countries are sitting between two tectonic plates? Oh, and Thomas felt the earthquake in where he was living in Gippsland. Excellent. Okay. And someone was asking about lapis lazuli, so I can hold some up at the moment. This is a big piece of lapis. You can see the layers and that beautiful blue color. So lots of countries are on the edge of plates. So if you have a look, and I can share that map with you again later on, you can just actually have a look. So we've got areas where things are pulling apart, and we've got areas where things are pushing together. So I will actually show you a little bit more detail about that in a moment. How many crystals do I have? Oh, Mike, I've probably got hundreds in my collection, varying in sizes from really little ones that I take out to schools to really big ones that I keep safe at home. Okay, let's keep sharing the slides. So, and because I've got a few more experiments to show you at the end as well. Okay, that's our convection current. And again, this is that mechanism of how this engine of what's happening inside the Earth. So we've got that convection current pulling apart crust under the ocean and on land, but also it's recycling. So just imagine the Earth is not constantly getting bigger. So it's not constantly growing, it's not shrinking. So wherever we get new crust being formed, we must have crust being recycled. And that's where we get these areas underneath, and that going into the mantle and that recycling and melting again. So let's have a little look. We've got a couple of different ways things are being formed. So the first one of these transform faults. So imagining the edge of those tectonic plates. One, they are sliding past each other. Now, it's not smooth. They get stuck. And when they release pressure, that's when we get earthquakes. And we'll share the video if you missed the earthquake session by Geoscience Australia this morning. We'll put that in our follow-up as well. So this is a big jolt, a big movement of the two plates or faults, and that's releasing that pressure. And this information, apart from the fact that sometimes we can't feel it, but we do pick it up on the sensors. And it is one of the ways that we know what the inside of the Earth is made of, because of the waves. As they move through the Earth, they move through solid and liquid material differently. So that is how we've been able to map that inside of the Earth, to know that it's a solid core, a liquid outer core, and that sort of liquid mantle. Okay, we're going to skip through this to this place here. So this is the Ring of Fire. So it's the most geologically active place around the world. And this is where we get most of the volcanoes and earthquakes happening. So the blue lines are areas that are called trenches. The deepest place on the ocean, the Marianas Trench, is 11,000 meters deep. And that is in this area. So these are areas where the crusts are pushing together and one is sinking and it's being recycled. And as that's being recycled and melts, it bubbles back up, forming volcanic arcs and chains of volcanic islands. A lot of these active volcanoes are actually under the sea. So especially around here, we get a lot of eruptions. You might have remember the big Tongan volcanic eruption earlier in the year, where lots of pumice was blown out as well. This was felt quite widely, and that pumice eventually will float and it will hit the east coast of Australia. So I'm actually going to show you a piece now. That's a piece that I got not from that volcanic eruption, but from another Pacific one that had actually floated and washed up onto the shore, where I was able to collect it. And I'll show it to you closely in a moment, because it actually had marine worms living on it. As it was floating, it became a habitat, and one of the ways that these organisms can move around the ocean. So this area is really important. If you notice, all of those blue lines are areas where the crust is being recycled. So the Pacific Ocean is actually shrinking. So this is an area where those crusts are being recycled. So that the whole Pacific area is getting smaller. And it's the Atlantic Ocean and the mid-Atlantic ridge which is pulling apart, making new crust being formed. So that is getting bigger, and the Pacific Ocean is getting smaller. So that's our tsunamis being formed by a big jolt inside from an earthquake. So these are our what we call a divergent boundaries. These are areas where they're pulling apart, like the mid-oceanic ridge that I just mentioned. There are a couple of places on sort of continental masses that this is happening. The Rift Valley in Africa and up in Iceland, where the continental crusts are pulling apart. But mostly this process is happening under the ocean. And our convergent plate boundaries where they are pushing together and one has to recycle. So I'm going to jump forward a little bit just to have a little look at our volcano. So just before, we're going to do a couple of questions, then I'm going to do some experiments, and then hopefully we'll have time for a couple of more questions as well. Just got to release the gas. You might be able to hear it now. Oh, no, not too bad, because that was getting very bubbly. Just going to pop it out of the way. I'm not sure where to put it without knocking over a rock or the next experiment. So just wanted to show the idea of these volcanoes and what is happening in a volcanic eruption. So you can see it behind me as well, that I'll focus on in a moment, is that magma chamber filling up. And that's being filled up from the mantle, and inside starts forming pressure. So a volcano that has erupted regularly doesn't have as much pressure as, say, one that hasn't erupted for a long period of time, and that pressure builds up. Scientists can actually map the outside of the volcano and put sensors on it to see whether it's bulging or moving. They would be tracking the earthquakes that are happening nearby and associated to the local faults or the tectonic plates. They're checking gases that are coming out of the volcano and any changes that are happening. But if there is a big eruption, I'm going to show you two different types of eruptions in a moment: a shield eruption, which is more of a lava flow, or a big stratovolcano, this explosive eruption. But the key things I want you to have a look at is this big eruption column. So as material is pushing up into the atmosphere, more and more material is coming out of that magma chamber and is filling up that column. Now, once that is empty, there's no more material pushing up, and we get gravity, and it drops back down into what's called a pyroclastic flow. And that's by far the most dangerous part of a volcanic eruption. And we can see a couple of pictures here. So that's the eruption column dropping back down the side, and we can see an enormous pyroclastic flow in this photo here. So I'm just going to stop sharing. We're going to do a couple of questions while I get ready for my hopefully not too messy experiments. So I'm just going back to the Q&A. Does every mineral or rock have variations? No, not always. Sometimes they are just, exactly the same, but others will have color variations depending on where they're formed. What is the strongest mineral? Well, that is diamond. So diamond is by far, in that hardness scale, the hardest. So, and it gets used. So a lot of the diamonds that actually are being found are used in industry. So they're not used in jewelry. You get a lot of industrial quality minerals as opposed to gem quality. So a lot of the diamonds are used to make diamond tip drills for digging and all sorts of amazing things. I do not have a black diamond, AJ. That would be quite nice. What elements are commonly made? So a lot of them have oxygen linked with them. So a lot of the quartzes, silicon dioxide has oxygen linked. So that's a very, very common one. Taylor's asking how much a diamond's worth. It depends on the diamond, depends on the color, depends on how clear it is and how big it is. So there's lots of questions about how expensive and how cheap. Well, the cheapest rock, Mrs. T, would be the one that you find outside in your backyard on the way home from school today. That will be the cheapest rock. How do you know which metals are in the Earth's core? Okay, so they have done tests of those kinds of things to work out what they think it's made of, and also, linking to what other planets are made of and what meteorites are made of and all sorts of things. How do we know when the New Zealand volcanoes will erupt? Well, exactly the way I just mentioned, doing testing. So they're going to be mapping the outside, they're going to be testing the gases, the temperature, if there's lots of earthquakes, but it is not an exact science, that area in volcanology, in studying when earthquakes and volcanoes and things like that are going to erupt. So sometimes they need to use the best scientific evidence and data they've got to make estimates, but it's you can't predict it to a day. Let's have a look. Do rocks have salt? So yes, salt is actually a type of mineral. So it's called an evaporite, and you can get lots of different types of salt. It just happens that one type of salt we use is our table salt, which is sodium chloride, but there are lots of other types of salts that can be formed at a specific type of formation when something evaporates. Are the biggest volcanoes on Mars? Oh, I don't know the answer to that. There's certainly the biggest volcano on Earth is actually underneath the ocean at the moment. Where did I get all my rocks, minerals and crystals? I have bought a lot of mine. Some things I've collected when I was on university field trips and things like that, but most of mine I've either gathered and collected if I've picked up something I've really liked, or some of the more crystals and minerals I have actually purchased at different mineral fairs and those kinds of things over a very, very long time. Remember, I started my rock collection when I was 4, so I won't tell you how long I've been collecting for, but it is quite a while. Okay, so I think, how many volcanoes are there in the world from Liam? Well, Liam, there are a lot. And some of them, as I mentioned, are under the ocean. They haven't even escaped the surface yet. So some of them, we don't even know what we do know about them, but they are very, very small. So they are constantly forming. And some of the old volcanoes, if they haven't erupted, would be eroding with that weathering. So wind and rain would break them down, and their sediments would end up forming a sedimentary rock later on. So that rock cycle that we talked about and those plate tectonics, think about long time, that long-term cycle. So we talk about it in the geological time scale, which is a slow process. Okay, guys, let me show you a couple of things. Hopefully I won't make too much of a mess, but I'm pretty sure I will. So the first thing we're going to talk about is the different things that come out of volcanoes. We talked about rocks, gases, and ash. So this experiment is looking at some of the gases. So inside this bottle, I've got vinegar with a little bit of food coloring. And in this balloon, I've got bicarb soda. Okay, so bicarb soda is something really common you can buy in the cooking aisle, and it's in this balloon just to separate them at the moment. So we're going to see if we can blow the balloon up. So I'm just going to scroll out for a minute. Okay, I'm holding on to it really tight so it doesn't pop off. So ready? Everyone can call out for me. Ready? 1, 2, 3. And you can see it bubbling. It's not clear anymore. The balloon is getting bigger. If I hold it, we can actually see that it's ended up going into the balloon. It's erupted. Now it's bubbling even more. You can hear it bubbling away. That was just where my microphone was. And it's settling back down. We've got our 2 colors separating out again. It stopped bubbling and we've blown our balloon up. Now, this is not an effective way to blow balloons up for a party or anything like that, but it is just a way to demonstrate that sometimes we get a reaction. And in this case, we've got a clear gas. Now, if you were doing this at home, not that this is the way it happens in a volcano, but my bottle and balloon are actually a bit cold now. So this particular scientific reaction absorbs heat. So it's left everything behind feeling a little bit cold. So essentially it is just bicarb soda and vinegar reacting together, and what's left over is a gas. So a lot of the times with volcanic eruptions, we can't see those gases. Okay, so a lot of times, of course, there'd be very hot gases, but they would be going up into the atmosphere. So one of the things that can happen after a volcanic eruption is acid rain, because there've been lots of sulfur dioxide gas going up into the atmosphere. Now, luckily, what I've got here is just plain old carbon dioxide. I'm going to try not to make a mess. And you can hear it. There we go. That is the gas, carbon dioxide gas leaving the balloon. So it is a clear gas. This one's really harmless, but other gases that come out of volcanic eruptions, not necessarily harmless, can interact into the atmosphere and can cause long-term effects after that. So let me just move this one out of the way. My speaker. And I'm going to get my tray up there. So question there, does the gas produced from a volcano considered to be pollution? So there would be lots of carbon dioxide gas going up into the atmosphere as well. We would be, sorry, I've got it all over my glasses. There would also be issues with sulfur dioxide gases and those kinds of things. So yeah, it would be considered atmospheric pollution. We've had this issue with really lots and lots of volcanic eruptions, you know, the ash and the gases, you know, blocking out the sun, you know, causing global climate changes. That certainly happened in the past. Okay, so let me see if I can somehow manage to get all of this in the camera together. So I've got two eruptions. The first one I mentioned I'd show you is a shield volcano. So this is a nice, gentle eruption. And for those of you that need to go, I'll try to be really quick. I understand you'll be able to watch this on the recording if you need to finish up for the day. Okay, so I got my shield volcano here. Inside is baking soda, some food coloring, and I've got some more vinegar. So we're just going to have a look at the eruption here. So it's lava flows. So as the eruption happens, the lava flows out and over quite gradually. Different eruptions will make different layers within the volcano, but you can see it's not a big explosion. It is a lava flow. When that lava reaches the ocean, it's going to cool and slow down. So these shield volcanoes are not considered to be as dangerous as, say, the next one I've got here, which is my big type of explosive volcano that'll have that pyroclastic flow. I'm just moving it all the way over because I'm going to make a mess. And we're going to finish up with this one here. Oh, I need to take the lid off. And I'm going to have to scroll all the way out. So apologies for the back of my office here because we're going to make a mess. So here's my volcano. Try to get out of the way a bit. So we're going to count down from 3. We're going to see how high we can get it here. So I'm going to move all the way to the back. I have to scroll all the way out. Let's see. So ready? 1, 2, 3. Oh, I've got to mix up my flow. 1, 2, 3. Everyone's being quicker than me. Oh, we can see it bubbling over. I was being too gentle. Oh, that could have been a lot bigger. I was being too timid, everyone. I was worried about making a mess and getting it all over my computer. So I didn't explode it quite enough. So let's see if I can get the last bit in. You can see as it's trying to explode, as I'm putting in. I've also got some detergent in this one as well. So you might have been able to see how the bubble is really foaming away because of the detergent. So when you try this experiment at home, try different combinations of bottle size, the amount of vinegar, the amount of bicarb soda, adding detergent to some and not others, because my detergent is still bubbling over even now. And I've got a massive tray of bubbles here. So thank you so much for joining me today. It's been wonderful to share some of these amazing ideas of what is going on inside the earth. We will share the video with you as well, and the videos of all of the sessions from today. So remember, this is just the beginning of your journey. Go out there, explore, collect rocks, learn about them, get a hand lens, look at the different crystals and all sorts of different things. There is lots of information out there for you to discover more about earth science, more about rocks and minerals, and to start your very own collection as well. So thank you so much again to Geoscience Australia for supporting us today. And thank you all for joining me today, and have a great afternoon. Bye, everyone.